Title of Module 2, Analysis of Algorithm Efficiencies. Here we want to find the best way to study algorithm efficiencies. Yeah. In our early lectures, I said execution time not stable, right? Execution time, if we use that to, study the algorithm efficiency, it's not stable. Yeah. So later we find a better measure. That's the basic operations. Basic operations. Yeah. Sometimes, multiplications, sometimes comparisons. Basic operations. So that's a more stable way. Yeah. But next question is, when we use basic operations, so we have a function to represent the number of basic operations. For example, for the selection sort, we have a number. Yeah, so here, let me use the selection sort as selection, as an example. In selection sort, the number of comparisons we need is 1/2 times n minus 1. Okay? Yeah. Here. Yeah. So this is the function. Yeah. All right. So we want to look at this function. We want to use the main part of this function to represent the efficiency of this algorithm. Okay? The main part. Yeah. We may want to drop the minor parts. Some minor part, not that important. Yeah. We want to drop the minor part. So this topic here, we introduce the growth functions. Growth function is the simplified version of this. Yeah, this function still not very simple. Not very simple. So we want to make it as simple as possible. We only take the most important part of this function. So we call it the growth function of this algorithm. Yeah. All right, so let's look at the, how do we extract the most important term from the given function. Yeah. Formula between running time and the number of basic operations. There is a relationship, running time function and number of basic operations. These two functions are closely related. First, we want to see what's the relationship. Yeah. Yeah. This section is pretty abstract. Yeah. So we need to, use some abstract notations to study the algorithm efficiencies. Yeah. Notations. First, we define running time function T of n. T of n. We know it's unstable, but we just, here, we use this function. Let's assume we work on the same machine. How about that? Okay? Yeah. We use two different measures on the same machine. Running time measure, basic operation measure, these two on the same machine. Yeah. All right, yeah. Function of the number of basic operations used, we use C of n, two different functions. So what's the relationship between these two functions, T of n and C of n? We want to connect them. Yeah. There must be some relationship, right? Yeah. So the operation, the basic operation, the meaning, right? Yeah. So last time I mentioned a little bit. Yeah. Here, let me give you the meaning of this basic operation. The operation contributing the most to the total running time. Yeah. For example, in our polynomial evaluation problem, multiplication contributes the most, right? Yeah. Addition contributes very little. Yeah. So we can ignore addition part. We only take the multiplication part. So we treat multiplication as the basic operation in that example. Okay, yeah, yeah. All right. So for other algorithms, then you need to look at, so what operation contributes the most? Yeah. Yeah. All right. So in our selection sort, comparison contribute the most. Yeah. Other than comparisons, you have assignment operations, right? Yeah. Because you assign one value to a variable. So that's an assignment operation. Okay? Yeah. So you have a few other operations, but comparisons contributes the most. Yeah. So that's the basic operation. Yeah. All right. Then, to establish the relationship between these two functions, we need this number. Execution time of a basic operation. We use the constant C op. Yeah. Yeah. One basic operation, you clock it on a machine, so you should get some number, right? How much time you need to run that basic operation. Yeah. People may argue, yeah, at different time, that because you run basic operation, several times, you may get different numbers, right? That's highly possible. Okay, yeah. Same multiplication, different time you run, the amount of time, execution time may not be the same. Yeah, yeah. Sometimes more, sometimes because your CPU, your CPU does a lot of work at the same time, right? Yeah, yeah. Your CPU, works on many different things. Yeah, yeah, yeah. So if that happens, we just take average. So we get several numbers, then we take average. So we get the C op, this number. Then we can write the formula. Okay? Yeah. We take approximation approach, because it's very hard to get a very accurate expression. We can only approximate, use our formula to approximate the number. So T of n approximately equal to C, little c op times capital C of n. Each basic operation takes this little c amount of time, but we have total C, capital C of n number of basic operations multiplied together, approximately equal. Okay, yeah? So that's the relationship. And we treat this little c op, it's a constant. Constant. Yeah. So these two functions, you can see the connection between them, just the one constant connect them. But this constant should be associated with the current machine. The current machine will work. Because when we move to a different machine, that little c constant will be different. Yeah. Yeah. All right. So, yeah. All right. So here you can see proportional. The relationship between these two functions. Proportional. Yeah. Yeah. Then, yeah. So C, so this one we treat as a stable measure, yeah, for an algorithm. Yeah. That T, not a stable measure. Yeah. All right. And then, because these functions, yeah, so the C functions, usually it has several terms. Okay? Yeah. Several terms. For example, the previous one, 1/2 times n minus 1, we can write it as two terms. The first one, 1/2 n squared. Second, 1/2 n. Yeah, two terms. Yeah. Some functions we may need to use more terms, several terms. All right, So now, here, we want to simplify our function by ignoring some unnecessary details. Some details we feel less important, so we want to ignore it, simplify it. Yeah. We will do a few simplifications to make our measuring function as simple as possible. Yeah, that's what we want to do here. Okay, all right, yeah. Can we ignore some constant? Yeah. So here we have several constants. Yeah. So let's look at this question first. Can we ignore some constant, but still we can get the most important part of the function? Yeah. So we don't want to change the nature of the function. Yeah. We still want to grab the nature of the function, but we want to ignore some, less important factors. Yeah. So that's what we want to do. Yeah. Can we ignore some minor terms? Yeah. Some terms, minor. How minor? Yeah, we will see. How minor? Yeah. If we can ignore those minor terms. Yeah. Let's answer these questions before we can do simplifications. Yeah. All right. First, let's look at this ratio. When we do ratio like this, T of 2n over T of n, by this formula, you can see the C op, little c op can be canceled out. Yeah. So then it approximately equals to capital C of 2n over capital C of n. Okay? Yeah. Cancel the same constant. Yeah. And this formula is true on all machines, right? Yeah. Now after we cancel that little c op, then this relationship should be true on all computers. Yeah. Yeah. So that means we eliminate the hardware differences. Okay? Yeah. Hardware differences. Yeah. This ratio. Yeah. This ratio also can tell us how fast a function increases, right? Yeah. Every time we double the size of the data, then we take the ratio. If this ratio is large, then the original function should be increased in a faster rate, right? Yeah. Yeah. Because every time we double size the ratio, one is larger than the other, then the larger one should have the faster increasing overall rate, right? Yeah, we can see that. Yeah. We can see that. Yeah. Here, the good thing about the ratio, so people may ask, why you take the ratio? Good thing about a ratio is we can cancel the constant. The leading constant can be canceled out. Yeah. Think about, look at when we do this, the ratio. Yeah. So this function, yeah. Suppose this function is the f function. F of n equals that. Then we take f of 2n, f of 2n over f of n. When we do that, this 1/2 constant can be canceled out, right? This leading 1/2, because f of 2n there is 1/2, f of n there is 1/2. Both 1/2 you cancel out, right? Yeah. So that leading coefficient is gone. So if we look at this ratio, it tells us the leading coefficient is not that important. We can cancel out. Okay? Yeah? Yeah. Yeah. After you cancel out that leading coefficient, this ratio can still tell you how fast this function increases in some way. Yeah. Okay? Yeah. So from this, the observation of this relationship, so you can see now, we can simplify the original function by ignoring the leading coefficient. How about that? Leading coefficient. Yeah, because we just take the most important part. Leading coefficient we treat as, less important part. Yeah. So, yeah. All right. So that's the, one simplification. Then we want to do another simplification. Yeah. Here. All right. Another simplification. Yeah. 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 Here, this ratio, we already, we understand the constant part can be ignored if we want to further simplify the expression. Yeah. But how about, because there is a minor term. The first term we know much larger than the second term, right? Yeah. All right. Yeah. So we want to look at minor term, major term, and a minor term. Yeah. Question. What is the major term in that efficiency function? Yeah. Two terms in that example. Yeah. All right. The major term, so let's look at the major term. We also call a dominant term. That term dominates other terms. Yeah. Yeah. For example, this one. The first term, can you see the first term dominates the second one? Yeah. Yeah. So let's try to understand that part. Yeah. All right. In the selection sort, yeah. So we have that expression. Yeah. We have these two terms. Yeah. All right. The first term, that's the dominant term. This whole term we call the dominant term. And this term dominates the second term. Yeah. How does it dominate? Yeah. We want to understand how the major term dominates other terms. Yeah. Yeah. How to understand that dominance. Yeah. Because how do you measure that dominance, right? Yeah. Yeah. So here we want to view the dominant term. Yeah. How do we view? We take a ratio of the two terms. Ratio of the absolute value. We don't look at the negative sign. Two positive terms, absolute values. Yeah. When we take a ratio of these two terms, then we take a limit when n goes to infinity. Because we want to see the long-term, the future trend. So we let n goes to infinity, the future trend. Okay, yeah, all right. Yeah. After simplification, we calculate limit of n when n goes to infinity. Not simple, that's just infinity. So here you can see the limit of two terms, when n is very large, it goes to infinity. It's also very large. Also very large. Okay? Yeah. So based on this limit, now we want to understand the dominance question. Yeah. The first term, second term. Okay? All right. So let's consider, suppose this circle represents total execution time, total amount of execution time. Okay, yeah. This, whole area, circle area. Yeah. Then, which part is used for the dominant term? Which part is used for the minor term? Yeah. So we can draw, this very small part for the minor term. Then all the remaining part, all this, very big part used for the major term, the dominant term. Yeah. Yeah. How much is the dominance? Yeah. So let's think in this way. Okay. When n is 100, this minor term only takes about 1% of the whole execution time, right? When n equals 1,000, then this part becomes 0.1%. How about that? Then we can make n larger and larger when the n equals 10,000. That little portion becomes 0.01%. How about that? Yeah. It becomes smaller and smaller. All right? The question, can we ignore? Yeah, because this amount approaches to 0, right, when n is large. The percentage for the minor term approaches to 0. Can we ignore it? For the long run, in the long run, can we ignore it? Yeah, because when n is very large, that part can be ignored, right? Yeah, because when we study algorithm, we mainly worry about when the data size is large. When data size is relatively small, our computer can handle well, right? Our computer very powerful. So we don't worry about a relatively small data size. But we worry about large size. Our computer, we may need a lot of time to find the result. Yeah. So our main concern is when n is large, right? Yeah. So here, when n is large, the minor term can be ignored because the percentage is so little. If you ignore it, you do not lose much, right? If less than 0.1%, then you don't have problem to ignore it, right? Yeah. So now you can see we can ignore the minor term. If we identify the dominant term, we know it will dominate other terms in some way. So all the other terms, if we eliminate them, we won't sacrifice much. Yeah. Only we lose very little. Yeah. Less than 0 point something 1%. Question. Yeah.
Yeah, I just want to, so in this case it's kind of clear what the dominant term is, but is there a hard factor to determine it, or?
Hard what? Hard factor?
Yeah, is there, when you're considering what the dominant term is, is there like a formula you can use, like the ratio of time to figure out like what you should focus on, or
Yep.
is it more fluid?
Yeah. Here we do the ratio. Yeah. Here we do the ratio that tells us, amount of percentage of the portion it takes in the overall response time, execution time. Yeah. 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 So we treat, So you can treat the total time as 100%. Yeah. Then each term, it takes a portion of it. Yeah. So you look at that portion over whole amount of execution time, the percentage number. So dominant, that ratio close to 1. You will see, when we talk about dominant term, when n is very, very large, the dominant term takes the percentage close to 1. That dominant, right? Then we don't have question. We just make n very large. Sooner or later, that block, that dominant term, the block occupied by the dominant term, close to 1%. 1, that's 100%. Close to 100%. Okay, 99 point several nines %. That dominant. Okay, here you don't have problem. Infinity. Then n over 1. N goes to infinity. That one, too little, right? That one, too little. Yeah. So that kind of dominance, we don't have problem, right? Yeah. We don't have problem. Yeah. All right. Yeah. So now, after this round analysis, we can throw away all minor terms. Only keep the dominant term after this analysis. Yeah. All right, only one term. So we simplify the function a lot, okay? So we only keep the dominant term. Yeah. But from the previous slide, we take ratio double size, function over itself. This leading coefficient can also be simplified, all right? Yeah. Although so your argument, actually this leading coefficient is more important than minor terms, right? Yeah. Yeah, because that number, yeah. But here you can see, if we look at the f of 2n over f of n, we just look at the, increasing rate. We don't need that leading coefficient. We don't need that in leading coefficient, okay? Yeah, yeah. Because here we take this approach, all functions, we ignore the leading coefficient. All dominant terms, after we extract them from the original function, we all remove the leading coefficient. We only take the remaining part. So here we will use n squared, only n squared left after we do 2 rounds of simplification. The first round cross out all minor terms. Second round remove the leading coefficient. So only n squared left. And this time we think this n squared represents the most important nature of the original function. How about that? N squared. So this original function, it's an n squared function. How about that? We treat it as because the most important nature of that function is n squared. Okay? Yeah. Yeah. N squared is simple. Yeah. So this n squared, we call it the growth function of this function. So that's this concept. So we want to use a simple function to see how fast it grows. So we call it the growth function. That's our definition of the growth function. Okay? Yeah. 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 All right. Yeah. So then when we compare, because the important simplification we are doing here is later when we compare 2 algorithms, we just compare their growth functions. How about that? We only compare the growth functions of 2 algorithms and see which one is faster, which one is slower. Yeah. So many times they are the same. If 2 algorithms have the same growth function, then we put them in the same category. Okay? Because they're in the same category. Okay? Yeah. Their increasing rate pretty much the same. The function, you double the size over the original function, you get the same rate, right? Yeah. You get the same rate. So we put it in the same category. Okay? Yeah. All right. Yeah. So here we get this growth function concept. Yeah. B.2, compare growth functions. Now, we use calculus. We take the limit. We do the comparison. We need to use the limit. Okay? Yeah. In calculus. Yeah. All right. Compare 2 growth functions. Remember our algorithm, the problem number 5 we just solved the last time. Problem 5, that's the element uniqueness problem. And we did it using 2 methods. Let's get the growth functions from those 2 methods first. Then we compare these 2 growth functions. All right. Which method is better? We compare these two. Yeah. Method 1, this is the growth. Yeah. Method 1, we do not do any preparation. We just do comparisons in many rounds. So the worst case, because the worst case is this function. Yeah. The same as the selection sort. Yeah. This is method 1. Method 2, we sort the array first. The preparation step, when we sort the data, we need to pay this much. We need to do this many comparisons, n log n. Yeah. N log n comparisons. Yeah. Then after that, n minus 1 comparisons. So we add them together. Yeah. Now, the first step, we want to extract growth functions from these two functions first. Yeah. The method 1, yeah, we just did it from the selection sort. Here, the same thing, n squared is its growth function. Method 2, minor terms can be ignored, right? Yeah, yeah, minor. Leading term already 1, so its growth function just n log n. Here, the log means log base 2. Log base 2. Yeah. Okay? All right. The next thing is we want to compare these two growth functions. Which one is faster? Yeah. Which one is increasing faster? Yeah. Here, the concept here, we should be careful. When a function increases faster, the corresponding algorithm will be slower, right? Yeah. Because function, that means the number of operations grows more, right? Faster. So a faster algorithm, we want the fewer number of operations. Yeah, not more operations, fewer operations. Yeah. So here, when you read the question, you should read carefully. Do we want to know the growth function increases faster or the algorithm faster? Because the answer is opposite. Yeah. Opposite. Yeah. Yeah. All right. So here, which method is better? That means the one grows slower would be better, right? Yeah. The growth function that grows slower would be better. Yeah, not faster, better. Yeah. All right. The ratio. Yeah. So when we do comparison, we take the ratio. Yeah. We take the ratio. Yeah. Compare two growth functions. Yeah. All right. Here, let's take the limit. N squared over n log n. We calculate this limit. Yeah. And we can do cancellation, cancel out 1n, and simplify the limit to n over log n. Yeah. When n goes to infinity, yeah, what's the limit? What is the limit? Right? How to calculate it? Yeah. Think about that. Yeah. Okay. Yeah. All right. Yeah. So here, we can consider general log function. Yeah, not necessary too for just the constant a, but this a we want it greater than 1. Yeah. Not necessarily integer, could be non-integer. We only need it greater than 1. Yeah. We want to compare these two functions. You know, yeah. How to calculate this limit from calculus. Okay, yeah. So the answer here, yeah, first I tell you the answer. The answer is infinity. N over log n with any base, if this base is greater than 1, its limit is infinity. Can you see that? Yeah. Yeah. So from calculus, yeah. So we can see it in different ways, in a few different ways. Okay, yeah. All right. How to see it? Yeah. Method one, we do some variable substitution. Here, because when we see log, so most people do not have a good idea on the log function. How large is a log function? Okay, it's hard to see it. Okay, yeah. We know when n goes to infinity, log function also goes to infinity, right? Yeah. So both the numerator, denominator, all go to infinity, but one is faster than the other. N function goes faster than log function. Yeah, but how do we see that? How do we see that? Yeah. Let's do some simple variable substitution first. Let us use a variable u to represent log base a of n. Log base a of n. Introduce a u function. Because after this substitution, the log is gone, right? The log symbol is gone. So when we get a better idea, if we eliminate log, we can see the function better. That's the idea. Yeah. All right. Now, n equals exponential function a to the u. Exponential function. Okay? Yeah. So let's go back to the original ratio using our new variable substitution. We represent this limit to a to the u over u. How about that? Can you see the ratio a little better? This a is greater than 1. Can you see the numerator increases much faster than denominator? Because the numerator is an exponential function. All right? Do you know an exponential function? Yeah, the base here, the base greater than 1 is important. The base greater than 1 is important. If less than 1, then it does not grow, right? It's decreasing. So the base greater than 1 is important. Okay? Yeah. All right. A greater than 1. Then, have you heard of something like the exponential function always grows faster than any polynomial function? Have you heard of that? Yeah. People call exponential growth. Exponential growth is always faster than polynomial growth. Have you heard of that? Yeah. Exponential, okay? Eventually, it will beat all other polynomial functions. Yeah. All right. Yeah. To see why, we can prove it. Yeah. But one thing that people always say, in our daily life, well, you have an exponential function, it dominates all other polynomial functions. Okay? Yeah. All right. From that point of view, you can see it's infinity. Okay? Yeah, it's infinity. Yeah. Because here we use this fact. An exponential function dominates any polynomial. This fact. This can be proved. Okay? This can be proved later. Yeah. Yeah. So here, after variable substitution, so we can see that. All right. All right. Next, now I want to use rigorous math to prove it. L'Hopital's rule. Yeah. So in calculus, there is a technique called the L'Hopital's rule. We can calculate the limit using derivatives to calculate limit. Here, so let me, help you recall this technique. Yeah. Sometimes we need to use. Yeah. In order to understand a few things, we need to use this L'Hopital's rule. Yeah. 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 But in our assignments, I will not assign you L'Hopital's rule questions. Yeah. You do not need. Yeah. But when we understand some of our results, we need to use it. Yeah. Okay. Yeah. Method 2. Yeah. We use L'Hopital's rule to calculate the limits this time. So we can do it rigorously. Yeah. All right. Limit of ratio of two functions. Yeah. When we calculate limit of two functions, that's the situation we may need to consider the L'Hopital's rule. Yeah. So let me, basically, this limit equals the limit of ratio of two derivatives under some condition. We need to check some basic condition. If the condition does not hold, we should not apply L'Hopital's rule. Yeah. So what's that condition? Yeah. Yeah. The condition is the ratio we treat as indeterminate form. Indeterminate, it's called indeterminate form. Not determined, indeterminate form. Okay? So what's the indeterminate here? Numerator goes to infinity, denominator goes to infinity. Their ratio is not determined, right? Yeah. Because the ratio could be anything, right? The ratio could be infinity, the ratio could be certain number, the ratio could be 0, right? Yeah. So from that point of view, we say the ratio is not determinate. So we call it indeterminate form. Yeah. So L'Hopital's rule can only be applied to this kind of indeterminate form. Yeah. So first you need to check if it's an indeterminate form. If it's not, you cannot apply L'Hopital's rule. Okay? Only when it is an indeterminate form you can apply. Yeah. All right. Another indeterminate form is 0 over 0. Because the result could be anything. Yeah. 0, the numerator approaches to 0, denominator also approaches to 0. What's the ratio? Could be infinity, right? Could be some number, and it could be 0. It's not determined. So we also call it indeterminate form. Okay? Yeah. All right. And then there are several other indeterminate forms. Yeah. In calculus, yeah. If you can remember some materials from calculus 2. Yeah, not calculus 1. Calculus 2. Yeah. So you may still remember a few other indeterminate forms, like 1 to the infinity. Okay? The base is 1, or approaches to 1. The base approaches to 1, not exactly 1. Then exponent approaches to infinity. Yeah. It's indeterminate. Yeah, this, could be a lot of things, right? Could be infinity, could be a fixed number, and it could be 0. Yeah. You don't know, so that's another indeterminate form. Okay? Yeah. And another thing like, several other things. Yeah. Indeterminate, several. Yeah. Yeah. But for this class, we only consider the first one, infinity over infinity indeterminate form. Yeah. Yeah. Because our growth functions can only grow to infinity. So both numerator, denominator, both go to infinity. Yeah. So that's the one we consider. Okay? All right. Yeah. So if that's the case, we can apply this L'Hopital's rule. Now, here, let me show you the L'Hopital's rule application. Yeah. All right. So let's apply it on this ratio first. Yeah. U goes to infinity. Yeah. All right. First, both numerator, denominator go to infinity, so it's an indeterminate form. So we can apply L'Hopital's law here. Yeah. When we apply L'Hopital's law, we need to take the derivative of the numerator over derivative of the denominator. They are equal, so we write equal to, apply the formula. Derivative of the numerator, that's natural log of a times a to the u. The formula, derivative formula. So you can find it easily. Yeah. Then denominator, u derivative just 1. U just 1. Okay, derivative. The power rule of the derivative. U to the first, by power rule, it's 1. Okay, yeah. Now, after one round, here we apply L'Hopital's law, 1 round. Now you look at this. It's not an indeterminate form anymore, right? Yeah. Yeah. It's not indeterminate because you can see the result immediately. Yeah. The limit of this one, infinity. Yeah. Yeah. Numerator goes to infinity, denominator is 1. So the whole fraction goes to infinity. Yeah. Denominator 1, so it's gone. Yeah. 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 So here you can see by L'Hopital's law, you can find that a to the u dominates u easily, right? Yeah. You only apply L'Hopital's law once. Yeah. Sometimes we may need to multiply L'Hopital's law many times. Here, just once. We can get an answer. Yeah. All right. All right. So, yeah. And here, another thing. Yeah. When we apply L'Hopital's rule, there is one little thing you need to be careful. That is, you need to make sure the variable is continuous variable, not discrete variable. Variable, we can have discrete variable or continuous variable. Discrete variable, it takes the discrete values. Like 1, 2, 3, 4, 5, that's discrete values. Continuous variable, the value changes continuously. Okay? From 0 to 1, anything in the middle between 0 and we can take its value. That's continuous change. Yeah. All right. Yeah. Here, let me show you this. Let me apply L'Hopital's law another time to show you what I'm talking about here, continuous variable. Yeah. Look at this limit. That's our original limit we want to take, right? Before we do substitution, we want to take this limit. Okay, yeah. We want to take this limit, all right, yeah. But here, the two functions, numerator, denominator, they are both discrete variables, right? And can only take consecutive integers. 1, 2, 3, 4. Consecutive integers. Yeah. It's discrete variables. Yeah. By the definition of derivatives, you cannot define derivatives for discrete functions. No definition for the derivative. Derivatives can only be defined for continuous function, not discrete function. That means if you want to apply L'Hopital's rule here, you cannot. Because derivative does not exist. How can you take derivative? Right? So you need to make it rigorous. You need to make it rigorous. Okay? Yeah. Yeah. Here, let me show you how to make it rigorous. Yeah. All right. How to change the discrete variable to continuous variable. We make that change. Yeah. Yeah. Now, we consider another similar fraction, this time x over log of x. This time, we make x continuous variable. X changes continuously to infinity. Okay? Yeah. Start at some number, so that's not important. Start number not important. Yeah. Then changes continuously, going up. Okay? Yeah. Then log function x changes continuously, going up. Yeah. This time, both functions, they are continuous functions. So we can define their derivatives. Okay? We can define their derivatives. Yeah. Now, this time, we can apply L'Hopital's rule. Yeah. All right, so let's take derivative. Derivative, x derivative, that's 1. Second, derivative of log function, yeah. So we have this formula, 1 over brackets natural log of a times x. That's the derivative of log function. Yeah. Here we assume we use base a. Log of base a greater than 1. A greater than 1, log of base a. Okay, all right. Then, after simplification of this limit, yeah, let's simplify it a little bit. Yeah. After simplification, we get this. Limit of natural log of a times x. Natural log of a, it's a constant. It's a positive constant, right? Yeah. Because a greater than 1, this natural log is a positive number. It's a positive constant. Positive constant times times x. But x goes to infinity. So the whole function goes to infinity. So we get the result. Yeah. We modify our original ratio, change the discrete variables to continuous variables. That's the only change we make. Then we can apply L'Hopital's rule to get its limit is infinity. The next question. After we get this result, can we go back there? Because our goal, we want to calculate the limit n over log of n. That's our original question. Yeah. Excuse me. Yeah. Can we go back? After we get a continuous version limit, can we go back to the discrete version of the limit? We need to make a last step. Last step. Go back from continuous variable back to discrete variable. Yeah. The answer is yes. We can make it. Yeah. Then we can say the limit of this discrete version is also infinity. Now the question, why? Why this step is legal? Why you say this step is legal? Okay, yeah. You need to justify it. Okay? Yeah. 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 So your intuition is right. Yeah. So intuition is right. Yeah. But here, let me use the definition of the limit. So we explain. We need to go back to the definition of the limit. Limit. All right? Yeah. So here we're looking at the limit. Yeah. Limit, let's look at this continuous version limit. When x goes to infinity, do we specify the way how does x goes to infinity? How does x go to infinity? Do we specify it? Which way? Because x goes to infinity, there are many different ways, right? Think about, is there many different ways x goes to infinity? Yeah, right? Yeah. For example, x can take 1, 2, 3, 4, this way to infinity. Can we take x 1 square, 2 square, 3 square, this way approaches to infinity? Right? Can we take, root 1, root 2, root 3, root 4 to infinity? Right? There are so many different ways. But here, x goes to infinity. Which way? In the definition of the limit. Original meaning of the limit. Anyway. Anyway would work. Okay? Anyway, if that way goes to infinity, it would work. That definition using the epsilon delta take care of that. Okay? Yeah. So here we do not go to the epsilon delta details. Yeah. But it take care of that. We just only need to know by taking the epsilon delta language, we take care of, any way x approaches to infinity is acceptable, is legal, right? Yeah. Here, we just take one particular way, 1, 2, 3 consecutive integer. It's legal, right? One of the many, many ways to infinity. We only take one special way. It's legal by definition of the limit. Any way is legal. We just take this discrete consecutive integer way. It's also legal. So we have this result. Okay? So that's the logical reasoning. Yeah. All right. Yeah, so here, I spend a lot of time here because I want to show you when we do logical reasoning, as some critical part, we need to do in a rigorous way. Rigorous way, okay? Yeah. Although I won't give you such questions in any assignment. Yeah. But for your understanding, you need to understand this much. Okay? Yeah. So then you feel comfortable, okay? All these results we can use in a comfortable way. Yeah, yeah. Another thing is, if you read a textbook in this particular part, it's not rigorous. Okay? So I fix a hole. The hole is the textbook applies L'Hopital's rule on this discrete function directly. Okay? If you read that part. Yeah. We know, so you cannot apply on discrete functions. Yeah. Yeah, but the result, still infinity. Okay? Infinity, but we're going back. After we get a continuous result, then we come back by the definition of limit to fix that hole. Okay? Yeah. Just let you know, yeah, when you read the textbook. Okay? Yeah. All right. So we finished this topic. Yeah. All right. Next, we have about 5 minutes. Yeah. So let me, yeah. All right. Yeah. Yeah. So the conclusion, we already know, yeah, second method is faster than the first one. The method is faster. Okay? Growth function increases slower. Yeah, with this growth function faster. But we say algorithm faster, not growth function faster. Okay? Yeah. So when you read statements, yeah, be careful. So what we are talking about? Are we compare algorithms or we compare growth functions? Okay? Yeah. So because the answer will be different. Yeah. Yeah. Read the questions carefully. All right. Next, I want to say something about the discussion of the project 1. Yeah. Here, last time I mentioned that the Java way to implement in order to overcome the overflow problem. In Java, we use big integer class. So you can search the online document, this big integer. So here, I want to explain a little bit why this big integer can overcome the overflow problem completely. Because when we have numerical values, when we use any numerical values, we always have overflow. Okay? Floating point, you may have overflow. Double precision, double, you also have overflow. So numerical values, you have overflow. Okay? But how does Java get around that overflow problem? Because it created a special class. It uses string to represent its value. String does not have overflow, right? When you use a string, because string you can represent digits, okay? 1, 2, 3, 7, 4, 5, 4, and so on. Can you put it in double quotes, make it a string? 9, things like that, right? So you make it a string object. When you could make a string object, there is no limit for number of characters in a string, right? In Java, no limit. If your computer can handle, all right? So no limit for the string. So they design this big integer. The underlying storage is a string value. The storage string to store the number representation in string format. Then it uses a set of special methods apply on the string form, all the operations, all the basic operations. Here, this version, when you construct, you specify the number of bits, the size. Because when you construct, you need to specify how many digits, right? Here, how many bits? Bits, the binary representation, how many bits? And the second one, you can make a random big integer number, okay? Because you just put some random object there, you can generate a random. For our project, we want to generate random data. Our polynomial coefficient should be random. Our x value also should be random. So we need to use this, random way to generate our data. Okay? All right. So these two. After that, then we apply certain operations. Here, add, how to add two big integer, based on the string storage representation. This class take care of that. So we don't need to know that, right? We just call dot add, big integer object dot add. So you can study, study a few examples, web search, find some examples. Pretty straightforward. You make a big integer object, that object dot add another big integer object. Parenthesis, another big integer object, so that the values added up. Similarly, for multiplication, multiply. Okay? One big integer object dot multiply another big integer object, then their values multiplied. Okay? If you want to take the value, print out the value, long digits. On your computer screen, so you see thousands of digits. Okay? Very fast. The computation is very fast. You hit, you see it immediately, very fast. Okay? Yeah. All right, so let me stop here for part B. Yeah. And after I post the quiz, I will send announcement. So you will see it, let you know. Okay?